SpaceX just broke the 300-ton thrust barrier. While Boeing's rockets sit grounded with delays and failures, Elon Musk quietly achieved what engineers called impossible. The numbers are insane. Raptor 3 already delivers 280 tons of thrust. Now Raptor 4 pushes past 300 tons, more power than most countries' entire space programs. But here's what Boeing can't figure out. How does SpaceX make engines more powerful while cutting costs in half? The gap between them isn't closing. It's becoming a chasm. What makes this engine so different? And why can't anyone else even come close? Let's dive right in. The impossible foundation, Raptor 3's hidden power. So how does SpaceX make engines more powerful while cutting costs in half? The story starts with what they already achieved. And it's more insane than you think. Raptor 3 delivers 280 tons of thrust. That's enough force to lift a Boeing 747 straight up with no runway. But the real shock isn't the power, it's the pressure. Most rocket engines explode at 200 bar of combustion chamber pressure. Raptor 3, it runs at 350 bar, day after day, without failing. We're talking about pressure that would crush a car like a tin can, contained in a space the size of a trash can. The metal walls are under stress that would snap steel cables, yet they hold. How is this even possible? The answer changes everything you think you know about rocket engines. While Boeing burns fuel once and throws away the exhaust, SpaceX burns everything twice. They create hot gas to spin the turbopumps, then burn that same gas again in the main chamber. Zero waste, maximum power, pure genius. But 300 tons of thrust? That's where the physics get deadly. The death zone. Why 300 tons should be impossible. Here's what rocket engineers discovered decades ago and why they gave up trying. Every time you increase thrust, the forces trying to destroy your engine don't just increase, they multiply. At 300 tons, you're not dealing with 20% more stress than 280 tons. You're dealing with exponential destruction. The Russians learned this the hard way. Their RD-170 produced 800 tons of thrust, but needed 4 separate combustion chambers because no single chamber could survive the forces. Even then, it failed constantly. Boeing took one look at this problem and quit. Their SLS rocket uses 1970s space shuttle engines because they couldn't develop anything better. 4 ancient engines, just to get 16% of what one Raptor 4 delivers. But SpaceX didn't quit. They found something nobody else discovered. The breakthrough came from an unexpected place: jet engines. Specifically a material called Inconel. This nickel-based superalloy can handle 2,000 degrees Fahrenheit without melting. But Inconel has limits. For Raptor 4, they had to go beyond limits. They're using 3D printing, not just to make parts, but to create impossible internal structures. Instead of welding pieces together where they could fail, they print entire sections as single components. No seams, no weak points, no failure. But even that's not enough for 300 tons. There's something else, something SpaceX hasn't revealed publicly. Secret weapon, sweating metal. Every rocket engine faces the same killer problem. The combustion chamber gets hot enough to melt steel in seconds. Traditional engines pump cold fuel around the chamber walls to cool them. It works, barely. But at 300 tons of thrust, even the best cooling systems fail. The heat is just too intense. That's when SpaceX did something incredible. They made the metal itself sweat. Instead of just flowing fuel around the chamber, they push fuel through the chamber walls. The metal becomes porous, literally sweating fuel to stay cool. The fuel absorbs the heat, then gets burned for power. This is technology that NASA researched for 50 years without success. SpaceX cracked it in their factory. Why does this matter? Because cooling was the ultimate barrier to rocket power. SpaceX just removed that barrier completely. But the real miracle isn't the technology, it's the cost. The $750,000 question: how SpaceX broke economics. Early Raptor engines cost almost $1 million each. Starship needs 33 engines per flight. That's $33 million, just in engines, for one launch. Completely impossible economics. Raptor 4 costs under $250,000. That's a 75% cost reduction while delivering 20% more power. How do you make something better and cheaper? The answer is SpaceX's Star Factory. While other companies hand-build engines over months, SpaceX prints them in days. Robots handle welding. AI detects flaws humans miss. 3D printers create complex geometries in hours instead of weeks. But here's the genius part. Instead of building engines to last 100 flights, SpaceX builds them perfect for 10 flights. Then they recycle them. This sounds crazy. Why not build engines that last longer? Because when you design for 10 flights instead of 100, you eliminate massive over-engineering. Lighter materials, simpler designs, cheaper production. And when your engine costs $250,000 instead of $1 million, replacing it after 10 flights is actually cheaper than maintaining it for 100. This is why Boeing can't compete. They're still thinking like it's 1970. The AI revolution. Engines that think. Here's where SpaceX did something no one expected. They gave Raptor 4 a brain. Traditional engines are dumb. They turn on, run at fixed settings, then turn off. If something goes wrong, they explode. Raptor 4 monitors hundreds of sensors in real time. If one cooling channel gets too hot, the engine automatically reduces thrust in that area while increasing it elsewhere. The engine literally adapts to save itself. It's artificial intelligence applied to rocket engines. This is how you get reliable reusability at extreme performance. The engine doesn't just survive, it learns. But the real breakthrough comes when you scale this up. The 37-engine orchestra, controlled chaos, current Starship uses 33 engines. Future versions will use 37. That's more engines than every other rocket in history, combined. Managing 37 engines simultaneously should be impossible. Each engine needs individual control while perfectly synchronizing with 36 others. One mistake, and 37 engines become 37 bombs. SpaceX solved this with distributed intelligence. Each engine has its own computer. They talk to each other continuously, making collective decisions about thrust. No single controller is in charge. But the system as a whole exhibits perfect coordination. It's like a flock of birds. No bird leads, but they all move as one. This is why engine failures don't matter. If one engine dies, the other 36 automatically compensate. The mission continues. The Boeing disaster, how giants fall. Let's address the elephant in the room. Boeing's SLS costs $4.1 billion per launch. It uses 1970s technology, it's not reusable, and it produces less thrust than Starship. How did one of America's largest companies fall so far behind a startup? The answer is philosophy. Boeing's approach is fundamentally conservative. They use proven technology, extensive testing, traditional manufacturing. This worked for decades, but it can't compete with SpaceX's radical innovation. Boeing builds engines like jewelry, handcrafted, over-engineered, incredibly reliable, but they cost 10 times more and produce 1/10 the power. SpaceX builds engines like smartphones, mass-produced, optimized, replaceable. Boeing can't change because their business model depends on government contracts that reward caution over innovation. They can't afford to fail, so they can't afford to innovate. SpaceX embraced failure. They built hundreds of engines and blew most of them up, learning what didn't work. That's why the gap keeps growing. It's not just technology, it's completely different ways of thinking. The Mars equation. Why 300 tons changes everything. But here's the real reason SpaceX needs 300 tons per engine. It's not about Earth orbit, it's about Mars. Mars has a unique problem. The atmosphere is too thin for parachutes, but too thick to ignore. You need massive thrust to land safely. With 300-ton engines, Starship can land 100 tons of cargo on Mars. That's enough supplies for a small colony in a single flight. But here's the killer requirement. The same engines that land on Mars must take off again for the return journey. Less gravity, thinner atmosphere, but also less fuel because you can't refuel initially. This creates an impossible optimization problem. You need engines efficient enough for the return trip, but powerful enough for landing. No rocket engine in history has solved this challenge. Raptor 4's full-flow stage combustion maintains perfect efficiency across all conditions. Earth launch, Mars landing, Mars takeoff. The same engine excels everywhere. This isn't just an incremental improvement. This is the technology that makes human settlement of Mars possible. And Boeing? They're still trying to reach the moon with 1970s technology. The gap isn't closing, it's becoming a chasm. And Raptor 4 just made it unbridgeable. So there you have it. SpaceX didn't just break the 300-ton barrier, they shattered every assumption about what's possible in rocket engineering. While Boeing clings to 50-year-old technology, SpaceX is literally printing the future. Engines that think, metal that sweats, 37 computers working as one mind. But here's what really blows my mind. This is just the beginning. Raptor 4 isn't the endgame, it's the foundation. When SpaceX starts mass-producing these engines, when they're landing on Mars monthly, when other companies are still trying to reach orbit reliably, the space industry won't just be different, it'll be unrecognizable. And that raises the ultimate question. If SpaceX can rewrite the rules of physics and economics this dramatically, what other impossible barriers are they about to shatter next? The next few years are going to be absolutely wild, and we'll be here covering every breakthrough, every failure, every moment that changes everything. What do you think happens when SpaceX inevitably pushes past 400 tons of thrust? Let me know in the comments, because honestly, I'm not sure anyone can predict what comes next. NASA spent 30 years failing at this. 24,000 tiles, 80,000 hours of repairs after every single flight. SpaceX just solved it in 1 hour. How? They threw out NASA's playbook completely. No more glue that melts, no more months of repairs. Just hexagonal tiles twice as strong, locked in with pins that won't budge. But here's what NASA never saw coming. These tiles work on Mars too. How is that even possible? Let's dive right in. February 1st, 2003. Columbia screams back to Earth at 17,500 miles per hour. The 7 astronauts inside, they have no clue that one tiny foam piece, just 1.67 pounds, has sealed their fate. 16 minutes later, they're gone. That foam piece hit a single heat shield tile during launch. One tile out of 24,000, and it killed everyone aboard. This wasn't just NASA's worst nightmare. It was proof that their entire system was fundamentally broken. Here's what haunted NASA engineers for decades. They knew the shuttle was a death trap. They knew those tiles were fragile. They knew the aluminum frame would melt if the glue failed, but they couldn't fix it. Why? Because they'd built themselves into a corner so tight, there was no way out. The 24,000-piece death puzzle. Every space shuttle heat shield was unique. Not similar, unique. 24,000 tiles, each one custom-made, each one hand-fitted, each one irreplaceable. When technicians found a cracked tile, they couldn't just grab another one off the shelf. They had to manufacture an exact replacement from scratch. Same size, same shape, same thickness, down to the millimeter. But here's the killer detail. These tiles were glued to aluminum. Aluminum starts losing strength at 480 degrees Fahrenheit. During re-entry, temperatures hit 2,600 degrees Fahrenheit. Do the math. If that glue failed, the aluminum frame would melt like butter in a microwave. So what was NASA's solution? More tiles, thicker tiles, better glue. Backup systems for backup systems. The result? 80,000 labor hours between every single flight. That's 40 people working full-time for an entire year, just to prep for the next mission. Every shuttle flight cost $1.7 billion. Most of that money? Fixing what broke last time. This wasn't space exploration. This was an impossibly expensive maintenance nightmare, masquerading as progress. But what if everything NASA knew about heat shields was wrong? The question that changed everything. While NASA engineers were drowning in complexity, Elon Musk asked one simple question. What if we threw out everything we think we know and started over? Instead of 24,000 unique tiles, SpaceX designed 18,000 hexagonal tiles with only 100 unique shapes. Instead of glue that melts, mechanical pins that lock directly into the steel hull. Instead of aluminum that gives up at 480 degrees Fahrenheit, stainless steel that maintains strength up to 1,500 degrees Fahrenheit. But here's the breakthrough that changes everything. Those hexagonal tiles aren't just stronger, they're designed to work together as one system. Square tiles have straight edges. Straight edges create gaps. Gaps let superheated plasma sneak through and torch whatever's underneath. Hexagons? They tessellate perfectly. No straight-line gaps, no weak points, no places for plasma to penetrate. It's like the difference between armor made of rectangular plates versus chainmail that moves and flexes as one piece. But even this revolution